I just to wrap this part of the chat up, I put a couple notes on comparison with other techniques. And I think what was most interesting to me about this paper, again, was kind of the idea of refinement, and I like the iterative notion. And I think the loss function idea is probably a nice step in the right direction, especially, when the underlying thing you're using is a black box model. So, neural network produces a symbolic result, and the refinement process is just adjusting that. Big place that came up with was deep symbolic regression. But unlike in deep symbolic regression here, refinement, we're taking that result and passing it back back through gradient descent. So I think that was kind of a nice twist to things. A different viewpoint is another way to look at this is you're using a neural method to approximate a symbolic result. And this has also come up in a few places. The idea is, student network, purely neural, no guarantees at all, as you all noticed. But it's giving a nice starting point for a symbolic procedure. And for those of you familiar with discrete optimization, all the time it comes up as, hey, start with a linear relaxation and then figure out ways, to tighten it and discretize those variables over the iterations. I kind of like that analogy here. I don't think you can make such formal arguments using neural networks in this way, but at least as a heuristic to kind of, put you in the right ballpark, I think there's some promise there. We saw this with the anchor model in DSP, but also it was in this idea of neural guided abduction in that Samsung paper that should have mentioned at the end of his talk, where they use the neural model in much the same way here, as this is your first approximation and they refine based off of that. Interesting, the AAAI paper, they showed they got good results doing that, but they also were a little bit cautious, and they warned that by using the neural model, that could kind of push the combinatorial refinement process toward like a suboptimal solution. And I think that's another thing to kind of keep in mind with that stuff. You can also view this as another way to add constraints to a neural architecture. We saw with LNNs, we put in the loss function a term dealing with consistency. And this additional term on how close it is to a sequence that meets the constraint is actually has a similar intuition when you think about it. Like I mentioned with the LNN paper, the IBM guys, even though they didn't test this out, they said, hey, it could be possible in gradient descent at each iteration to mess with the results to ensure consistency. Here with STL Net, they're actually doing that, although they're using a totally different architecture. And finally, there's this issue of dealing with infinite ground atoms. And this came up in the Shindo paper, that Divyagna and Jesse and Kusta briefed a couple of weeks ago, where in the Shindo paper, they wanted to add functional symbols to the language. And when you add functions around your constants in a logical language, you could have infinite ground atoms, because you could have, just arbitrary values in the arguments of your predicates. The Shindo paper, had techniques to come around that by leveraging the templates and generating the templates in a way that limited the grounding to avoid this. And I thought about this as a point here, because also in the reviews, one of the arguments against the paper was saying that, well, these guys don't really use STL. They just kind of turn everything into atoms. So you really could think of what they're doing as a first order logic. So they're like, well, and I think one of the guys said, well, LTNs already did that. I don't think that's giving them enough credit for their contributions personally, because they're addressing that issue. I think it's actually, kind of a good thing that they did it that way, because they also show that this is useful in other logics like LTL, where you don't have continuous variables all over the place. So